So welcome back to our master theorem, fifth lecture in algorithms. So basically we'll practice some solving some of these occurrences and find out what the complexity of these are. Again, a reminder, if you go to our Artus page, right, or right here, you can get the cheat sheet and you can get also the actual exercises, sort of say, as a helper here, right? The examples, MIT master theorem examples with solutions, right? Yeah. Also, I want to mention Tom Scott. I don't know if anybody has watched Tom Scott. I haven't watched his videos for a while, but he's pretty good actually, right? I don't know, is he active still? I don't know.
He left YouTube.
He left YouTube. Okay, yeah. He used to have good videos. Right, he still has them, but I guess he was burned out a bit, right? Yeah. So, but yeah, he has a video from a couple of years ago about big O notation. So it's pretty good. It's a link on our Artus page, so you might want to watch it at some point. It's like 9 minutes. Basically talks about how he wrote some horrible code, right? So, yeah. Okay. So now, let's go back to our master theorem. And again, remember, you have to, first of all, in order to actually use master theorem, we need this type of form, right? We need some work, the function which does the work, right? It could be x, could be 1, it could be a constant, right? And then we have a and n divided by b, right? It has to be over 1, b has to be over 1, a has to be at least 1, right? And then we have 3 cases. Well, actually we have 4 cases. We have the 4 cases where this doesn't work, right? And we say, okay, we can't tell, we can't tell what this, right? So a and b, right? So you check basically here, right? Log base b from a, right? And then you see, is it actually, is this more than this function, right? Than this function, right? Then this occurrence is most important. Then they might match exactly if our function is exactly equal to this n log base a and then log k, where k is at least 0, right? 0 or more, right? Then you have this combined when both sides are important. And the third one, which is the easiest one, and we'll start with that one, when this function is more important. And again, mathematically you say more important, you have the epsilon, which is at least over 0, right? Meaning the recursive calls, right? This tree does not grow enough to overtake the actual work being done. Now, let's do some practice, right? We'll do some practice. So, anyone want to do the first one, or do you want me to do the first one for you guys? I'll do the first one, right?
Okay.
I'll do the first one, and I guess I was going to do it on. We can do it on here, right?
Yes.
Okay. Yeah. Right, so practice, Right, so first of all, we need to decide which case it is. Right, the first one here, 3t n divided by 2 plus n squared, right? So n squared, that's quite a bit. So you look at the a and b. B is what? 2. A is, right? So this is b, right? This is a, right? We check. A over 1, right? At least 1, yes. B at least 1. Well, I mean over 1. It has to be over 1, right? Yes, that's correct. That's good. This looks like a normal work function, nothing fancy. Okay. Then we can use it. And again, once you have some experience, you can immediately tell which one is going to be, which case is going to be. But let's do it slowly, right? So we'll do n, right? N log base what? Base 2, right? Of, right? Here, right? Base a of 3. Right. So how much is that actually? Roughly. Okay. We can't, unless you're using calculators, which some of you might be using, it's probably like 1.4 or something, right? Or 1.3. I don't know. How much is it? Anyone want to run it? But it's not. It's certainly not what. It's less than what. But the crucial part, it's less than 2.
Yes.
Yeah, that's the most important part. So this is, I don't know. But it's not, because if this was 4, right, it would be 2 exactly, right? So So we can tell, okay, it's, you know, some epsilon, I don't know, like 0.5, something, I don't know, right? And then the means, what does it mean? Which case is it? Who has an idea? Which case is it?
Case.
Which one?
Case 3.
Yes, it's case 3, exactly. Because, yes, the epsilon is over 0, right? That basically means is this part here is less than this part here, right? So this part here, right, is less than this part here, less than 2, right? From here, right? Right?
Yes.
So, what the answer then is? Answer is? N squared, right? And you can say actually in theta here, right? You can write theta n squared, right? And that's it. And that's the answer. All right. So can we do this? Oh no, I can't. I had to do against. I had to quit, and you'll have to do a new one, right? You have to do this one. Or usually we do this on a blackboard. We can also do it here, right? Or you can just tell me who wants to do the next one. And how do I quit this thing? No. Or I want to do a new fresh one. What is this one? Ah, no, again. Yeah, this is not very friendly, but I guess we can do the straight. Yes, say. Yes, close. Okay. Okay, good. All right, and we do one more. Not very friendly. Okay, and then we have to do again. No. This is not a very good workflow, but I guess we can do it. All right, and I want to use a computer. Maybe we'll do it here, right? Or we can just basically sort of like pretend we do it. Right. But I guess I'll mix them up eventually, right? So, second one. Who wants to do the second one? Who feels, okay, who has an idea what second one is?
Well, it's likely the case 2.
Yes, it is case 2, right. It is case 2. Why? Because
logarithm
of base 2 of 4 is exactly 2, right?
Yes.
And it matches that, right? N squared. Okay. So the thing is, okay, so this part here, so log base of something, so k is 1, right? How do you log base of something of 1 is what? What's the answer? Right? So basically k, this part here, right? Right?
Yes.
So 0 basically it will be 1, right? To the log of something, right? So this k, right? So this could be 1 basically, right? When you do something, you raise something to the power of 0, right?
Wait, why is k 0?
Okay, because you're allowed to, right? So basically what it says, okay, so here's the tricky part, right? So this formula, right, is trying to account for the fact that it's possible, right? It's possible, right? There is some log inside. Basically there is the function, right, has a log of something inside this work part here. Remember, we are looking compared to the function, right? Usually there will be nothing here, right? Usually this part does not exist, right?
Yeah.
So that's what it's saying. It's possible there's nothing here. We'll see some examples when there's something there, right? But for now, in this case, right, k is 0 basically, right? We're allowed, right, that it's nothing. So basically, both sides match, and this is the tricky part here, right? If both sides match exactly, n squared, it's case 2. But then, so this means k was 0, right? Because there's nothing there, they were exactly equal, right? But the answer is not n squared, right? Answer is n squared, right? This part here. Oh, I can't, right? Oh, but interestingly, okay. But is this actually, but the question is, how does this work? How does this part work here? I don't get this part here. No, it works as a mouse then. So that part works actually. I could use this as a, so that actually I could use this as a, so this part actually works here. Actually, you can see this, right? So in this particular case, in our here, there's no log, right? There's just n squared, right? So this means 0, ak was 0, And the answer will be what? N, this part here is n squared, right?
Squared.
Log n, and that's it. Because k is 0 plus 1. So add one more.
What is the base of the logarithm? In the
Here, base is 2, right? So here, we don't know what the base, doesn't matter, right? It's a generic base, could be 10, it could be 2, right? It could be 5,000, right? We don't know the base, right? That's again, it's because remember, it's very generic, right? So that's maybe a little bit frustrating for those who like grew up on exact math, right? This is very approximate actually, right? Because we don't, basically says log of something, right? Log base something, right? So here, if this k is 0, this part here is 1, basically, right? We raise something to 0 power, right? We get 1, right? Anything, right?
yeah.
Yeah, so that's the whole thing. So basically, it's a way of mathematically writing the ability that there is possible, there's no log whatsoever, right? If there's no log whatsoever, like as in here, right? We still need to add this log plus 1, right? The answer will have the log, basically. Again, that's only if these both sides match exactly, right? In this particular case.
But why are they multiplying with the n in the first part? Where
Here?
no, a little bit further, a little bit to the right.
Here?
Yeah.
Okay.
What's there? N? Because in
Okay.
our case, it's
Basically, what it's saying, it's possible, right? This we are trying to find. We're trying to generate the function. We're trying to recreate this function, right? Right.
Yeah.
In this case, it's n squared here, right?
yeah.
Right.
Then n to the power log with the base.
Yeah.
A is.
So basically, you're saying, okay, in this particular case, there's no log. That means k is 0, right? Because to me, what's a little bit again. This k is a power. How many times you take the log n multiplied by itself? It's a power.
Well, the whole logarithm will be 1, but why is it multiplied then by n again?
Okay, no, that's okay. So basically, how I would write this, right? That maybe on power. Right? How again? This is basically saying how I could write this. Basically, it's saying it's this, right? It's log n to the power of 0. That's what it's saying, right?
Okay, now.
So yeah, which is equal to 1, right? Equal to 1, right?
Yeah.
In this case, right? It's basically n squared times log n to the power of 0, right? That's what it's saying.
Yeah.
And so it does not exist, but it's 1 basically, right? The answer. So this part here is 1 because this means k is 0, but to actually get the answer we need this k plus 1. So that's the hardest one, I think, right? Because it's easy to miss it sometimes. Okay. So how about third one? What the heck is going on there? This part here. Okay, maybe. Okay, so can I do this? Okay. So what do you think? Which case is it? Which part is more important? Intuitively, we are making for each problem of size n. How much work are we doing? What's the function? The work function, the f function. Which?
It's 2 to the power of n.
Okay, that's how much work we do.
Yeah.
And then we make a recursive call, a recurrence, right? Divide by 2 and do it over again, right? For half size. So intuitively, what do you think? So how much is a? 1. Very good. Excellent. Very good. Just checking if you are asleep or not, right? So it's 1. B is how much? 2, of course, right? Yeah. Okay. But so intuitively, right? So it all matches. This part here, that's a lot of work, right? 2 to the n, right? Exponential work, actually, right? I mean, I would not even need the master formula. If I see something like this, right? I can tell the complexity is going to be this 2n, right? This thing is going to dominate, right? This part, these calls, not important, right? So, but you could show basically, yeah. So basically, that we can't even, that this part here, right? Log of base 2 of 1, right? That's how much is that? What is that? Log 0, right? Yeah, it's 0, right? Yeah, exactly. Right, yes, log base of 2 of 1 is 0, right? Yeah, of course, right? So, I mean, it's going to be less than this part here. So the answer is, again, case 3. So it's case 3, this part here, right? Yeah. So question is, can I use this actually? Wait, I can use this hopefully? Yeah, I can. So here's a cheat sheet. Yeah. Somewhere here there's the answer. Somewhere here you can see. You can double check. Yeah, it's case 3. Yeah. Indeed. Yeah. All right. So yeah, it's interesting. I can use this as a mouse. Yeah, that's fine. Because I guess. All right. So let's do the fourth one, right? And you maybe saw what the answer is already. But here's the issue, right? This just looks weird, and you know. And again, luckily, good news is some of these occurrences. Basically, the good news is in practice you won't see something weird that just on exams, right? Or people who want to torture you, right? But not in real life. So. That's why I only ask one problem to solve. One problem is going to be usually one of these 3, right? Not something weird like. So for this fourth case, right? Right, we see here, right? So what's going on here? Well, where's the problem? Where is the problem? What do you think? Is the problem here, n to the n?
No, the 2 to the n.
Yeah, a is not defined. A is not defined. So you say, okay, we don't know what a is actually, right? 2 to the n. Right. Obviously, this is a horrible algorithm. I don't know what's going on. I think this is. I have a feeling it's an infinite loop because 2 to the n, right? Calls to divide the n divided by 2. I don't know. I don't think it's gonna go less, right? You make so many calls, it's gonna give an assignment to implement this type of algorithm. I don't know. It's probably just gonna crash the computer, but you'll have an infinite loop because this is already a pretty big number, right? 100 to the 100, right? You can't really do anything with this, right? I don't know. Let's say if n was 4, let's say we have n is 4. N to the 4, so we're going to make 16 calls. I guess it will stop at some point, right? And it'll be 4 to the 4. I don't know, but it's. I guess it will stop, right? At 4. We can do it for 4, I guess, or maybe for 8, right? 16 to the 16th, I guess we could, right? But 32 to the 32, probably not, right? That's pretty big already, right? So, yeah. So this is not a very good recurrence, not a good algorithm, right? Yeah.
But if we plug the a and b in the logarithm, then it.
But you don't have, because the issue is that this a is not. There's no a. A is 2 to the n here, right? And that's not allowed, basically, right? Here, a are constants. So that's a gotcha. That's why this fails. So yeah, you have to check if a and b are actually constants, and are they actually at least 1 for a, and b has to be over 1. And if that matches, then that's when you get out of bed, because you have to check first, right? This is worth actually doing anything, right? So how about the fifth one? So this one, what do you think? Which case? So what's a?
16.
Okay, very good.
Case 1 likely.
Excuse me? Case 1, very good, excellent. You guys are already, yeah, you're ready for the midterm, right? Yeah. So, case 1. So a is 16, b is what, 4, right?
Yes.
So, log base 4 of 16 is how much? 2, very good. So that means n to the 2, right? So we compare. So, case 1. N to the 2 minus epsilon here would be what? Epsilon would be 1, yeah, that's case 1. It's epsilon over 0, right? So that means, therefore, by formula, by master theorem, we see here, right, that it is n, and again, that's the answer, which is in this n squared, yeah. So basically, again, what the master theorem is telling us that these recurrences are very important, right? Right, this is actually where all the tree, right, is going to dominate the discussion. Now let's look at the sixth one. Let me see the sixth one. Yeah. Okay. And I think this might be the tricky one, right? Which case? And let's see if I remember correctly, right?
Number 3.
Well, is it number 3 or is it number 2? Let's take a look. I have a feeling this is number 2, unfortunately. Yeah, this is a tricky one, right? So a is 1, a is 2, b is 2, right? Log base 2 of 2 is 1. Okay. And then you see, right? And you say, okay, and this is where people fail, right? You say, okay, we have n, and we have n log n, that's bigger, right? That should be case 3, right? Well, unfortunately, right, it's not, it's bigger, yes, but it matches exactly this case, except in this is a case where k is how much? K is also 1, right? Because it matches. So basically, we can redraw this, right? Maybe, right? We can redraw this as n to the 1, right? N to the 1, right? But we add this log, right? We have one case of log, right? Multiplied by log, where k is 1, right? Because, again, remember this here, it's basically log n is basically, you know, n log n to the 1, k. That's k here, right? So that means that the answer is not going to be n log n, right? It's going to be n log n squared, right? Because we have to increase by 1. K plus 1, right, with this part here. We have to increase by 1. Right. And that's tricky. Let's double check. Of course, I might be completely out of touch. Yeah, it is. You see? So it's n log 2. We add one more, right? So this is the tricky one.
Is it just because there's a logarithm?
Yes. Yes.
So it's just like an exception.
Yeah, it's like an exception, special case, basically, right? Again, why is this special? Why is our logarithm special case? Because of course of this 3, right? Because it's again. So in this case, it's one more. And so this could happen in real life, I suppose, right? I don't know of any particular algorithm, right? But it means is because this is more than n log n, right? Because we have to multiply log n twice, you know, by itself, you know, square it, right? Again, remember this is sometimes again we don't know the base, right? It's basically this, right? N log n, right, or some base, I don't know, 2 or something, right? Squared, right? N, and this is so k plus in this case it's k plus 1, right? 1 plus 1. Are you clear on this slide?
Yes.
Yeah. How about everyone else? Some so? Still need some more practice. Okay. All right. But like I said, good news, this is the only formula you really need to know in this course, right? Yeah, so, and again, and there are like maybe like 2 or 3 exercises I'll make you do. Okay. Oh, here 7 is actually does not apply. Let's take a look. Why? You know, yeah. Okay, and this is again tricky because well, it's 1, right? And it says, okay, this seems like less than log n, but it's log n.
K has to be larger than
Yeah, no, yeah, and the thing is this, yeah, exactly, and this is like, it's involved, it's basically goes like, oscillates. Can I get, oh, is there a paint here? Oh yeah, I can draw here, right? Yeah. Oh yeah, cool. Right, so the problem here is that it goes like the growth function, right? It doesn't go like this, right? I'll make it some weird color, like what color? Red, or right? Basically, this n log n, right? I'll call it what? F, G, H. I don't know. I'll call it K or Kx, right? Is log n divided by log n, right? If you have a graphic calculator, you do it. You would do it, right? It will go like, I don't know. It will go like this, probably something, right? Right? I mean, I don't know. I mean, it might not be. It's like looks like sinus, but something even worse than that, right? Because log n, it's not gonna. You can't even make any. You can't do anything. You can't make any predictions, basically, right? It's not good for analysis, basically. I mean, you could analyze some other way, but not like this, right? So, Control Z. Can I do Control Z here? Back. File. Undo. How do I do?
Higher.
Oh, here.
The right to the.
This one? Oh yeah, this one is undo. Yeah. I can do this. Yeah, alright, so that's why this in this particular instance, right, this is not a useful one. Right, now let's go next one. Now, okay, alright, so this is actually, most likely I'll give you something like this on a midterm, right? This is probably relatively easy, tiny tricks. Okay.
So the answer is that you can apply the formula?
Yeah. Okay. Yeah. Not NA, not applicable. So number 8. So we have this case here, right? Right. So for each instance we do n to the 0.51 work. That's a little bit n to the almost square root, right? On we have this. How much is a? By now we know a is 2, b is 4. So base n for log base 4 of 2 is how much? 0.5, right? Exactly, because we need to take it, right? So which case is it?
3.
Let's take a look. Yeah, I think it says case 3 because 0.5 is less than 0.51, right? So this part here is more important, and it's easy, right? So something like that will be on the midterm, something like that. Yeah. And again, I don't know where you will have, but sometimes there are people who do the, come up with new algorithms, like really complex algorithms. Sometimes you end up with something like this, actually. Right, so let's do some more. We have like 8 more minutes. 9, okay. This looks a little bit iffy. Oh, well, I think the problem is we can skip this one, right? Because you don't have to worry about this part, because this part here, right? A is less than 1, right? Let's double check. I'm not. Does not apply a less than 1, exactly. All right. Okay. So this one here, well, again, this one again is intuitive. You don't have to even think about it, right? Okay, yeah, it's a is, okay, you can do it. Okay, so a is 16, b is 4, right? It's case 3. Why? Because
It's
n factorial.
very big.
It's very big, right? So so this is n squared, right? N log base 4 of 16 is n to the n squared, right? Which is obviously less than n factorial, right? So answer is n factorial. The cursive calls them. All right, one more maybe. Let me have a couple more. All right. Okay. Well, this is a little bit tricky, but let's see. I think this is solvable. Let's take a look. Okay. First of all, a is what? A is basically, okay, square root of 2, but that's legal. It's 1.4142 something, right?
Yes.
That's okay. So a is square root of 2, base is 2. Okay, does anything useful come? So log base 2 of square root of 2, of course 0.5, right? And then so how much is that actually? So what's the answer of that? Is that actually a reasonable answer? Let me do a calculator of that. On log n, of course, right? How can we solve this one? This one is a little bit, and I just simple log n by the way work, right? So there's not much. Well, a has, yeah, okay. I don't know which one is going to win. I think. Let me do this. Okay. If you remember high school algebra again, let's do a calculator, right? Let's remember this little trick, right? How you can make base of anything, right? Who remembers? There's a trick. I want the built-in Latvian calculator. Okay, right? So let's do not standard. We'll do we are scientists or programmers, right? Well, actually, let's do okay. So you have only 2 logs. You have log. Do you know what log is? This is log. I think believe log base 2. Let's take a look. Okay, so let's do 100. Yeah. Okay. No, it's log base 10. Okay, this is log base 10, right? So if I do 1000, this will be 3, right? Now this is natural logarithm. So you say, okay, but where is my base 2 log, right? So how can we make a base 2 log? You have you can use any.
There was this theorem.
Yeah.
You have to take
logarithmic identity, and it's usually if you take your exam, your 12th grade exam, it's usually on the formula page usually, right? So you probably have forgotten it already.
You take the logarithm.
Yes.
At the base, so with any number and with the 1 or.
Yeah. And it's not this. There's a bunch of them, right? But you want. Where is it? This. Where is it? Yeah. I believe no. There's a bunch of them. Oh, changing. Okay, this is it. Okay, yeah, changing the base, right? all A and B. Or what do you do in discrete structures? You're learning about all this stuff, no? The quantifiers. Have you learned about these?
No, not yet.
Not yet. But this is, you know what this means, right?
Yes.
It's for all A and B, which are part of real numbers in this case. As long as A and B are not 1, I guess, all X are part of real numbers plus positive numbers, I guess, right? You can do this. So this is, again, we use for calculators, right? ln and log 10, but we don't have for base 2, right? So we want base 2, right? So we basically going to cancel out. We want base 2 out of something, right? So let's prove it. Let's take it out of 16. So it should be 4, right? Let's calculate this. So what you can do, I'll show you a trick, right? So this is a trick. So I want to calculate logarithm of base 2 of 16. Answer will be 4, right? We already know it, so we'll check. I'll show you magic, right? So I'll take some number. I'll take 16, right? 16. Well, first let me clear everything, right? So 16, logarithm of 10 is going to be something like 1 point something, right? 1.2 something, right? Divide by 2 logarithm this, and it's going to be 4. That's the trick, that's the identity, right? So we can calculate any. So okay, with that knowledge, right? With that knowledge, let me go to the PDF, right? We want to calculate this monster here, right? So base 2, right? And we have square root of 2, right? So base 2 is going to be the last. So we take. First of all, let's calculate square root. Where's my square root here, right? 1.4142, right? Okay, I remember my math correctly, right? And we'll take log base 2 or log natural, doesn't matter. Okay, so log, right? Divided by 2 log, right? Yeah, equals 0.5, which is actually as I expected, right? If you were doing it, right? So yes, okay. So that makes sense, right? Because to get if you think about it, right? How do you get a square root of 2, right? You raise 2 to the power of 0.5, right? That's the right answer, 0.5. So 0.5, right? So the question now is we have n to the 0.5, right? And the question is that the square root of n, basically, right? And log of n, which one is bigger actually now, right? And I have a feeling that square root is bigger, right? My feeling is, am I right? Let's take a look again. Yes, do you think so?
Yeah.
Yeah, square root is bigger, right? At some point, right? It's you know. So let's see so this should be which case? Meaning square root is bigger, it's going to dominate. Let's take a look if I am correct. If I remember correctly, but I know. Yeah, in this case 1, right? So log n, right, is less than square root of n, right? Okay. Now, one more, that's we're finished, right? So this one is easy. This one you can do, right? So A is what? A is how much is A here?
Base 2, base 3. Wait, no.
No, reverse.
Oh, reverse.
Remember, we start with A is first one.
Yeah, A is in the middle, so A is 3.
And this is 2, so base 3 or base 2 is how much? Well, how much the number is going to be?
Larger than 1.
Yes, so the answer is,
Case 1.
it's case 1 again, and the answer is going to be n to the base of log 2 over 3. You know, you can calculate. We can calculate how much it is exactly if you want, all right? And we can check. Yeah. Again, let's keep 2. Log, there's a base 2 basically here, right? So case 1. And I can calculate exactly if you want again. So how will I do it? Again, 3. I can do natural log, doesn't matter, right? That divided by 2 natural log. And it's going to be something 1.58. Because 2 to the power of 1.58 is going to be 3, basically. Right? You can calculate this. Let's see. Can I put memory? Right. recall, how do you call? Oh yeah, add memory. Okay, so to prove it, so 2, right? Recall, yeah. It's 3, yeah. It is. Okay, just a sanity check, right? Okay. So hopefully you got the idea how to use the master method, master theorem, right? They call it master method, master theorem, right? And again, there'll be 1 or 2 of these exercises at some point, right, in your future, right? So nothing too crazy, right? Basically, you know, in real life, again, what's fun is this theory, all this stuff, this theoretical stuff. In real life, of course, you'll encounter, but usually the case 1 or case 2 is usually the most often. Sometimes rarely you get case 2, right? And of course, you get something where the master theorem does not apply, right? So, okay. How do you feel right now about master theorem so far?
It's okay.
You can do it. It's not gonna kill you.
Yes.
Yeah. All right. So I'll see you guys in about half an hour. Yeah, half an hour, right? Yes. Do data structures.